Very happy to have Andrea Antinucci as a postdoc at Oxford, but visiting us via KITP. And he'll tell us about some recent work on constraining conformal defects. So take it away.
Thanks a lot for the invitation and for coming here. It's really great to be here. Today I will tell you about a couple of works. One that I wrote in December with Cristian Copetti, Giovanni Galli, and Giovanni Rizzi. And if I get time toward the end of the talk, I will get to tell you something about a work in progress with the same set of authors. The main theme of the talk is about extended objects in quantum field theory. Of course, all of us are familiar with textbook presentation of QFT, in which we mostly focus on local operators, particles, and so on. But QFT contains many more stuff. And indeed, it's not only about local operators, but can contain extended excitation, like strings or domain walls. And it also contains extended operators or defects. And I will give you more example in a while, but just to so extended operators are essentially operators that are supported not on a point, but on some submanifold in spacetime. And of course, the two concepts are not disconnected. Clearly, by acting with some extended operator on the vacuum, we create some state that is an extended excitation and vice versa. If you have some state with, some object with some gate charge that is massive at low energy, will produce some extended operator that can be thought as a word line or words volume of the state. And so there are connections between the two things, and we mostly focus on extended operators in this talk. And another comment is that there are a special class of extended operators that are topological, meaning that if you try to move them a little bit, nothing changes. And of course, yeah, topological operators. And in the model framework, all of them are regarded as symmetries. So yeah, any symmetry is something that is associated to some operator that you can move, say in time, and you will not change correlation function, but in a relativistic quantum field theory, you are allowed to move this operator in any way, and nothing will change. And for this reason, we associate the idea of having symmetries with the idea of having topological operators. And we use some of them, but most of the talk will be based on understanding extended defects, extended operators that are not topological. And just to give you some example that you can keep in mind in the talk and some motivation, there are various ways of presenting these defects. Roughly speaking, they are in two classes. One that I can call word volume presentation, where you explicitly write down defect equals something. And for instance, you can take some local operators and integrating on a submanifold, and you get what is called a pinning defect. So this is an extended defect that is constructed out of local operators. You can also have the Wilson line that are very familiar in gauge theory, or even more generally, you can construct defects by starting from your bulk QFT. Then you add some degrees of freedom leaving only on a submanifold, described by some defect theory, and then you couple the defect theory with the bulk. Now, the QFT in the bulk could be strongly coupled, could even not have a Lagrangian presentation, but this description requires that the defect have a microscopic Lagrangian presentation. This is sort of drawback that I will address during the talk. But as far as I know, this last presentation is sort of the most general that you can have. For instance, these two other things are special cases of this one. But yeah, I will be more explicit in the following. And there is a second type of examples in which instead of presenting defect equals something, you impose some boundary condition around the defect for the bulk degrees of freedom, and there are many cases, but I will mostly focus on this presentation. So, but for instance, boundary condition are a special case of that. A boundary can be thought as a defect between the theory and the trivial theory.
That's a quick question. So when you're thinking a defect, will require O to be a scalar, or carry indices?
It can carry indices with respect to the space, let's say rotation around the defect. This is allowed, but it must be a scalar on the word volume.
Awesome.
Right. So why do we care about defects? There are many reasons. First of all, they are there. So why not care about them? as I told you, they also have an interplay with extended excitations, and so it's interesting to study them. But even if you don't want to really care about the defect, they are very good probes of the bulk dynamics. So the typical example is Wilson lines. That depending on their expectation value, you're able to detect confinement or deconfinement. So by studying the QFT with the insertion of the defect, you learn something about the bulk dynamics. And relatedly, understanding which kind of defects and which kind of boundary condition are allowed in a given QFT can teach us a lot about many interesting properties of quantum field theory that are maybe property of the bulk theory, are not strictly speaking property of the theory with defect, but they are revealed in a very interesting way by understanding defects. This would require a sort of different talk, but just to mention that this is one possible motivation. And least but not last, defects are physically realized in many physical situations. For instance, they arise as impurities in many condensed matter systems, where now we can think about the defect as extending in time and changes the Hamiltonian locally. Okay, and there are many other applications that you might have in mind. So, as I told you, I will mostly use this sort of presentation that requires that I have a microscopic description of the defect, but then you can ask the following question: what is the space of extended defects in a given QFT? Namely, it's huge, because I can write down any defect theory and any possible coupling between the defect theory and the bulk. However, as I was already mentioning, along the RG, most of these defects that I can write down in the ultraviolet can flow to a trivial defect. So they don't really define a good non-trivial defect of my QFT. So, and this question above is not even well defined in a sense. So a much more well-defined question is, what are the universality classes of defects? So when I flow in the infrared, in the bulk I have some conformal field theory, and I can ask what are the possible conformal defects in this conformal field theory. So I can think about two different scenarios. Either I can fix some bulk CFT, and I try to construct defect in the CFT, and I can couple this defect in UV, and I can have an RG flow only on the defect. Or I can also have an RG flow that involves both bulk degrees of freedom and defect degrees of freedom. But the question we want to ask is to understand what are the possible endpoints of this RG flow. And we want to understand when we can define some non-trivial defect in a given theory. And roughly speaking, there are two ways maybe in which you can proceed. Either you start by a CFT in the bulk and a CFT on the defect, and you try to turn on some exact marginal deformation. This is clearly very hard, because when you have a marginal operator, typically when you add it to the action, this will get anomalous dimension and will no longer be marginal. I will come back to this question toward the end of the talk, but for now I will focus on a different type of strategy, which we turn on a relevant deformation, and we want to determine whether the defect in the infrared is screened or not. What do I mean by screened? A defect is screened if in the infrared it becomes essentially the trivial defect for the bulk theory. There is no correlation function, no experiment that I can do in the bulk that detects the presence of the defect. Okay? Typical examples are Wilson lines in gauge theories with fundamental matter. At low energy, the Wilson line is screened because the fundamental matter can screen the charge by a very long distance. Okay? And I want to convince you that symmetries can provide a very powerful tool to attack this problem. The typical example that, however, is not the one that we'll mostly discuss in this talk is higher form symmetries. So when a given defect carries some charge under some symmetry, this will automatically imply that if the bulk theory is a conformal field theory, then along the defect RG flow, the defect cannot be screened, because I cannot trivialize its charge. This is sort of obvious. And this is well known, but in this talk I want to discuss some more subtle situations in which the defect by itself doesn't carry some conserved charge, but some non-trivialization of the bulk symmetries will prevent the defect to be screened in the infrared. Okay? And I want to introduce some new concepts that will help us in understanding these sort of problems. So I will first start by defining what for me means a defect to be symmetric, to respect some bulk symmetry. And this will also allow me to introduce the concept of tilt operator. And then we introduce this new concept, the concept of symmetry reflecting defects, the concept of defect anomalies that are the analog of 't Hooft anomalies, but for tiers with defects. And then in the last part, I will mention this work in progress in which I can say something about defect conformal manifolds. Are there questions on the plan and motivation?
So just to get it clear, like for you, a defect is any extended operator in the theory?
That's right.
So what about in the CFT where you have like extended objects within the CFT, like for example, light ray operators or things like this? Do you also call those defects?
That's right, yes, that's right.
But they're defined within the CFT, so you don't even have to like trigger an RG flow.
Right, I mean, sometimes there is no RG flow, but sometimes there might be. So the example that you're mentioning is a special example, but for me, a defect is any kind of operator that is supported on an extended manifold. Sometimes you can just define it and it's what it is. In other situation, you turn on some operator on the defect, and if this operator is relevant, this defect, even though the bulk is a conformal fit here, this defect doesn't preserve the conformal symmetry that is preserved geometrically by the defect, and you have an RG flow. Just the couplings on the defect can run. Okay? I will discuss some examples. Other questions? Good. So let me start with the simplest possible example. I consider our QFT with a U1 symmetry, and I have a conserved current. And out of this conserved current, I can construct a topological operator. This is supported on a codimension 1 manifold. If this is space, this is just the integral of the J0 component of the current, but I can take more general manifolds. And this operator is a topological operator that generates this solution. Good. Now I consider my QFT with the insertion of a defect. And I want to ask whether the defect preserves or not the symmetry. What do we mean by that? In general, when I insert the defect, the word energy of the bulk gets modified. So it's still valid, far from the defect, but close to the defect can be violated by a term that the most general form is that there is a delta function localized on the defect times some operator. And by dimensionality, we realize there is a p-form operator, or if you dualize it on the word volume, it's a scalar operator on the word volume. And this is called the tilt operator. Okay. Now, if we are in a defect CFT, meaning that both the bulk and the defect are conformal, then the dimension of the tilt operator is protected and is equal to P. This is an exact marginal operator. So even if we add it to the action, we don't generate an anomalous dimension, and we get a defect conformal manifold. I will come back to this point at the end. But now we want to instead ask when, so in this situation, I will say that the symmetry is broken by the defect. Why? Well, because the operator that is topological in the bulk, if it crosses the defect, it fails to be topological. In particular, the junction between the topological operator in the bulk and the defect is no longer topological. I can move the defect provided that I don't move the junction. And this is essentially described by this equation. Okay?
And just to be sure that, but there does exist a topological junction with the defect of one type. Oh, maybe the defect without this deformation on one side and the defect with the deformation on the other.
I don't understand the question, sorry.
In other words, like as you sweep the topological operator past the defect,
Right.
you will leave behind the integral of this.
I will change the defect. That's right. I mean, another way we can describe this equation, this picture is that when you pass the defect with the topological operator, basically you will modify the defect by integrating the tilt operator on the whole defect. So this also helps you in understanding that there is one special case in which the tilt operator is non-trivial, but it can be a total derivative, and then this integral is 0. And this suggests that when this is the case, we should be able to construct a topological operator even in presence of the defect. And indeed, we can do that. In this equation, we call this the defect current, and we can construct a modified topological operator by dressing the bare junction with this kind of object here. And you can easily check, it's like a 30-second computation, that now, in this situation, even the junction becomes topological. So now we are able to move the defect around and even when we're able to move the topological operator around, even when it intersects the defects, it will stay topological. And this is the situation that for me is the one of symmetric defects. Okay, is the definition clear?
Do you require like star J to like GD to be globally well defined? Like you could have some kind of transcendence from each thing.
Right. In that case,
Fractional probability.
no. In that case, the symmetry is not preserved.
Okay, okay.
This should be a well-defined lookup. Then we can discuss more subtle cases. It could be that, right. But strictly speaking, in that case, with this definition, it will not be topological.
Right.
Yep. Now, okay, this is the general definition of symmetric defects, but now I can require an even stronger condition. So let me focus on codimension 1 defect. This can be generalized. Some of the things that I will say can be generalized to higher codimension defect, but for concreteness, let's focus on codimension 1 defect. And I can require that on top of being symmetric, even the pullback of the current on the defect, so this in component is just the perpendicular component of the current on the defect, this by itself is exact. And is the differential of some other defect operator. This is in general different from the tilt operator that I discussed before. And you can realize, if you like this language of topological operator, that under this assumption, not only the topological operator can cross topologically the defect, but it can also end topologically there. Now, let me emphasize this fact that I'm sure that people that are familiar with topological operators are very, they know this very well, but maybe not all of you are aware of this, that whenever I have a topological operator, I can always try at least to cut the operator and defining on a manifold with boundary, but in general, the boundary will not be a topological operator. It can be a topological operator only if the symmetry acts trivially, right? Because otherwise, the topological operator acting on a local operator, if I'm able to cut the operator topologically, then I could remove it, and then I will trivialize the action. So the only situation in which I can cut topologically a topological operator is when it acts trivially. So if I assume that my symmetry acts non-trivially in the bulk, then it shouldn't be possible to end this operator topologically. But what I'm requiring here is that it can end topologically on the defects. And this end line is topological. Equivalently, I can ask that the topological operator is absorbed by the defect. Okay? This is a stronger condition than the one I was discussing before. And I will call defect with this property symmetry reflecting defects. It will be clear in a while why we use this name, but let me give a disclaimer that in a previous version we used a different word. We call them strongly symmetric defect, but we realized that there is a clash with the other names in the literature, so we decided to change this name. And it's a stronger condition than just being symmetric, but the two properties coincide for boundaries for a very simple reason, because a boundary is a defect between the theories and the trivial theory. So if a defect if the topological operator can cross the defect, of course it can end there. So it's sort of obvious. But precisely for this reason, the so-called factorized defects, namely defects that you can construct out of products of two different boundary conditions, are in particular symmetry reflecting, because this is essentially a defect that is the product of two boundaries, so it can end on each boundary, and it's automatically symmetry reflecting. This concept is a sort of generalization of the idea of factorized defect if you only restrict the symmetry sector. So this defect behave as boundary where we look at the charge sector of our theory. In a sense, they are sort of mirror for the charge. We have, instead of having charge conservation in the whole theory, we have two charge conservation on both sides of the defects. So for instance, if we have this defect and we try to throw some object against it, if the object is not charged, it might go through or might not, but if the object is charged, it must be reflected. Okay? So this is why we call it symmetry reflecting defects. Is this clear? Okay,
Can I ask for
Yeah.
it says a product of two boundaries, you mean product of two symmetric boundaries, like symmetry preserving boundary?
right, that's right, yeah.
Oh,
That's right, yeah. Good. So before telling you why this concept is interesting, let me first show that it exists. Let me discuss this very simple example. I have a 2 plus 1D U1 gauge theory in general with matter. That is the action. And I can construct a two-dimensional defect by adding on a two-dimensional manifold a compact boson, a two-dimensional compact boson with given radius that is coupled with the ball shown is this coupling phi f. F is the field strength of the U1 gauge theory. The coefficient here is required to be quantized for gauge invariance. Now, as is well known, three-dimensional gauge theories, abelian gauge theories, topological symmetry, you want topological symmetry, that is there just because the field strength satisfies the Bianchi identity, and the current is just this one, and the monopole operators are charged under this symmetry. Very good. So why is this defect symmetry reflecting? It's very simple, because if you look at the equation of motion of phi, this is what you get. And it's exactly the question that I had before. It's exactly the question. So the current, the pullback of star J becomes exact on the defect. This is the operator, right? So what I'm saying is that this defect that I find this way in the UV, it must be symmetry reflecting, and this property must be preserved along the RG. So this theory in bulk, in general, is a very strongly coupled theory. So if in the limit of a very large number of matter field, it becomes weakly coupled, but otherwise it's a strongly coupled CFT. And here I'm giving this Lagrangian presentation in the UV, and who knows what happened in the infrared. So we analyzed this problem in the paper in the large enough limit. You can look at the paper for that. I will not have time to discuss it, but in that case, we were able to verify something that I will mention in a second. But for lower values of NF, who knows? Because the theory is extremely strongly coupled, so this is a strong prediction for the theory. And so let me go to why we are interested in this defect. First of all, I mean, you can be interested in this defect just because of the property that I just mentioned, that they behave as mirrors in the charge sector. So this is kind of a huge property that they must reflect all the charged objects. But for the purpose of what I was mentioning at the beginning, to understand what is the space of extended defect in QFT, they are very interesting objects because they cannot be screened in the infrared. Why? Well, if you start from the definition that they can end topologically on the defect, so the defect allows the topological operator to end topologically there. Then if you run the RG and you assume that the defect becomes trivial in the infrared, you run into a contradiction if the symmetry acts faithfully in the infrared. Because as I just told you, you cannot have a topological operator that acts non-trivially, but can end topologically. Because here, this becomes like the identity operator. So this is a contradiction, and you can prove that this cannot be possible. So if in the UV we define a symmetry reflecting defect, then we know that whatever happened is a very robust property, because this defect must stay there in the infrared. Okay? However, there are two possibilities in general. Either it flows to a non-trivial conformal defect, or it could also flow to some topological defect that, however, must be a non-trivially acting symmetry of the bulk theory. It must be a non-invariable symmetry of the bulk theory. So you have these two options. So this is not a trivial defect, because it's a topological defect, but it must have some non-trivial interaction with the bulk.
I mean, but this defect may not be, could be non-simple.
That's right, that's right. Yeah. So I would like to be able sometimes to decide between these two options. And to do that, let me introduce a different concept now. This can be applied to both just symmetric defects or symmetry reflecting defects. And it's the concept of defect anomalies. And it's just the analog of truth anomalies, but in defect QFT. So the model point of view on truth anomalies for standard group like invariable symmetries is that I can have some QFT with some global symmetry. I try to couple it to background field, and I perform a background gauge transformation. And it can happen that the partition function is not quite invariant under this transformation, but it's a phase that cannot be cancelled by modifying my theory by local counter terms. But what happens is that anomalies for internal global symmetries can always be cancelled by inflow with a one-dimension higher classical theory with a certain action coupled to the background field, with the property that this action is gauge invariant on closed manifold, but fails to be gauge invariant when I put my theory on manifold with boundaries, and the gauge variation is a term that precisely cancels this anomalous variation here. Okay. Now I can try to do the same in presence of defect. You can easily convince yourself that if I consider a theory with the insertion of a defect, I do the same. First of all, I have to assume that the defect is symmetric, because if it is not symmetric, there is no way of coupling the theory to background field. I can only couple the theory to background field if the theory has a symmetry. But after I couple the theory with the background field, I can ask whether the partition function is invariant under background gauge transformation or not. And in general, on top of the bulk term that I was discussing, you can also have a term that is localized on the defect, right? So this is very simple, but curiously enough, we were not aware of any other discussion on this point. So defect QFTs can have anomalies that are only there because the defect is there, that are not anomalies of the bulk. But exactly as anomalies for QFTs, they can also be cancelled by inflow, but now the inflow is some theory of one dimension higher than the defect. So you can think about it either as a theory embedded in the bulk inflow, or if you like, you can also embed it in the bulk spacetime, but it's localized on some manifold that ends on the defect for volume. You have this action here that cancels the defect anomaly. Okay. Let me just give you a simple example to let you understand what I'm talking about. Consider again Q83. It's not very important that we are in 3 dimensions. And as a defect, let me consider the Wilson line. So suppose we also have n charged boson with charge 1. Maybe you might think that the global symmetry is SUN rotating the bosons, but the center of SUN is actually part of the gauge group. So the actual flavor symmetry is a quotient of SUN divided by Tn. That is this PSUN. Okay. Now, a quotient group can have more bundles than SUN. In particular, you can couple the theory to a background field for this flavor symmetry. Let me call this background field A. There is a background field for PSUN that, however, cannot be lifted to a background field for SUN. Right? This is like having a fractional instanton. PSUN can have fractional instantons. And this is measured by a certain characteristic class, degree 2 characteristic class. And the peculiarity of this theory is that if you turn on a background field with non-vanishing omega-2, then you're forced to integrate in the path integral over gauge fields, the dynamical U1 gauge fields, whose Dirac quantization condition is spoiled by a fraction determined by W2. Okay? Now, if you think about the definition of the Wilson line is written in this way. It's like the way you always write it, but doesn't really make sense because you cannot integrate connections. So one way to make sense of it is to define it by integrating the field strength on a disk whose boundary is the line. And why is this well defined? Well, because you always say this definition is independent of the choice of the disk. If I choose another disk, I actually get the same answer because the integral of f over a closed to manifold is a multiple of 2 pi. But that's not quite true if I turn on this background, because now the integral of f is no longer an integer multiple of 2 pi. But there is a way to correct it that is just subtracting to f this term here that depends on the background field. And after I do that, I can rewrite the Wilson line as a line operator. But I remain with this bulk term that is precisely an inflow for the defect. So we will say that this Wilson line is symmetric under the flavored symmetry, but that's a defect anomaly. Okay. Now, again, defect anomaly are invariant and must be reproduced in the infrared. However, they do not always prevent the defect to be screened in the infrared, because they can be matched sometimes by a decoupled quantum mechanics that has a projective representation under the symmetry. Actually, a bit of a more advanced comment is that they are not strictly speaking decoupled, because they couple only to the background field. So if you turn off the background field, then the quantum mechanics is decoupled, but they become coupled back when you introduce the background field. But maybe you want to ask something more. You want to ask whether I can really define a non-trivial defect in my theory. And sometimes you can have some extra inputs that ensure this non-decoupling. For instance, in this paper, they discuss some G function constraints. The G function is some quantity that is monotonically decreasing along the RG. And sometimes with some argument using this G function on top of the defect anomaly, you can be sure that the defect is not screened. And more recently, in this paper by Daniel, Theo, and Konstantinos, they pointed out that there is some correlator that you can compute that ensures you that the defect cannot be screened. But now what I want to discuss in this talk is how we can use defect anomalies to decide between the two options that I was mentioning before in the case of symmetry reflecting defect. Namely, whether in the infrared, the defect is an interesting non-trivial conformal defect, or it can flow to a topological defect. And I want to discuss an example in a very simple model that is the 1+1 de-Ising CFT. But to do that, let me give you a crash course on topological defect line in 1+1 de-Ising CFT. This will be very basic, but just to be sure that everybody is able to follow. So the Ising CFT has three primary operators, 1 sigma and epsilon, and correspondingly it has three topological lines, 1, eta, and n, with these fusion rules. So eta is a Z2 symmetry, n is able to absorb eta, while the square of n is 1 plus eta. So there is no inverse of n. That's the reason why we say that n is a non-invariable symmetry. And the Z2 symmetry acts on the primary by, so sigma is charged, epsilon is not. And the other important thing is that we can look at the twisted sectors of eta. You can think about the twisted sectors in various different ways. Either you put the theory on a cylinder and you put eta along time and you look at what is the Hilbert space on a circle. And so what are the states? And by state operator correspondence, you can relate them to operator living at the endpoint of the eta line. And there are three of them. One is called typically mu. It has the same conformal dimensions of sigma. The two are exchanged by primary Barnier duality. And then there are two Majorana fermions, one left moving and one right moving Majorana fermions. And among the three of them, only mu is uncharged under the Z2 symmetry. So if I on top of this put one other eta line around it, this will be uncharged, while the other two are charged. Okay. As I was telling, and on the other hand, there generates a non-invariable symmetry. You can see this by the diffusion rule, but also by the action of n on the primaries. N will send sigma that lives in the untwisted sector to mu that lives in the twisted sector. And relatedly, as you can see from already this diffusion rule, but also from this picture, n can absorb eta. So in particular, n can be thought as a symmetry reflecting defect, even though it's a topological defect for the Z2 symmetry. Okay, you can have this concept even for topological operator, but since it can absorb eta, so eta can terminate on n, this is precisely the definition of being symmetry reflecting. But that's not the example that I want to discuss. But it will be important to keeping this in mind. The final thing I want to say about topological defect line in the Ising CFT is that there is an interesting F symbol. An F symbol is some relation that you have when you create a sort of junction between various topological defects and you try to move this junction. And in general, you can have some phase. And here, the phase that will be interesting for me is that I can have a an M defect here and 2 eta here, because as I told you, eta is allowed to terminate here. But if I try to exchange the two, I get a minus sign. And if you think about it for a second, this is exactly a defect anomaly. So eta, N is symmetric under eta. It's also symmetry reflecting, but it has a defect anomaly. But under what symmetry? It's not under the Z2 symmetry, because you cannot have anomalies for Z2 symmetry on a line. This is an anomaly for a Z2 times Z2 symmetry. And this is a very important fact that indeed symmetry reflecting defect sort of double the symmetry, because they're able to distinguish between a symmetry defect from the left and a symmetry defect from the right. So whenever you have a symmetry reflecting defect that is symmetry reflecting to some symmetry G, the defect will actually fill a double symmetry G times G. And this is very important, that you can have additional anomalies that you couldn't have if you didn't recognize that the defect is symmetry reflecting. Said in another word, when we discuss anomalies, we want to start from our theory and couple it to some background fields. But the fact that for symmetry reflecting defects, some of the topological operators are able to terminate on the defect tells us that we are able to turn on more general backgrounds with respect to what we can do in the normal theory, meaning the theory without the defect. Because in the theory without the defect, we cannot terminate the topological operator somewhere, while with the defect we can. And these additional anomalies are detected by these more general background fields that we can only turn on in presence of the defect. Okay? Now let me go to the example that I want to discuss. Let me start in the UV. So of course, the Ising CFT is a conformal field theory, so there is no RG flow in the bulk. But as I was saying at the beginning, there can be an RG flow on the defect. So I start in the UV from a topological defect that is a non-simple defect, just 1 plus eta. And this is obviously symmetry reflecting, just because eta times this defect is the defect again, right? But now this defect is topological. I want to deform it with some relevant deformation and discuss a defect RG flow. And the relevant deformation that I want to discuss is this mu operator that I was discussing here. This mu operator that lives in the twisted sector of eta. So in general, you cannot deform some QFT with a twisted sector operator because it's attached to a line. You cannot integrate it. But now we can do it. We can deform this operator with mu. Why? Well, exactly because this defect here is symmetry reflecting with respect to eta. So since eta, the line to which mu is attached, is absorbed by the defect, I'm allowed to integrate this mu on the line. Is this clear? And on top of this, mu is not charged under the symmetry, because if mu was charged under the symmetry, I cannot integrate it over something that is constructed out of this symmetry operator. There is some divergence, right? Because it's not clear whether I'm integrating on the left or on the right, because I get signs. So yeah, it's very important that mu is uncharged. Now this is a relevant operator that's dimension 1 coordinate. So it will trigger a defect RG flow. This coupling here, this lambda here will flow, and we can ask what happened in the infrared. Does it flow to a trivial defect? Does it flow to a conformal defect or topological defect? Well, because of this picture, and because this defect is symmetry reflecting, we know that it cannot flow to a trivial defect. That's an immediate conclusion. But does it flow to a conformal defect or to a trivial defect? Or to a topological defect, sorry. If it flows to a topological defect, it must flow to some topological defect that is also symmetry reflecting. And I told you the full list of topological lines in the Ising CFT, and you can realize that the only two that are symmetry reflecting are 1 plus eta or n. Yeah.
Why can't I stack those with also an additional decoupled quantum mechanics?
Very good. In that case, you will get a larger quantum dimension, and this is not allowed. It's not allowed by the G theorem. And indeed, the G theorem does not even allow 1 plus eta, because it has the same G function of 1 plus eta. But so for the people who don't know, the G theorem is the following statement. you can compute some quantity that is called G function that is obtained by the logarithm of the free energy in presence of the defect. And this quantity has been shown to be monotonically decreasing along the RG. It's like the C function into the CFTs or the A anomaly for the conformal field theories. This is the analog for defect RG flows. It is only monotonically decreasing if the bulk stays a conformal field theory and we have an RG flow on the defect. And this is required to be monotonically decreasing, and it cannot stay constant if there is an actual RG flow. So if the operator that I'm turning on is relevant. So even 1 plus eta is not allowed. But is n allowed? So this G function for topological defect coincides with the expectation value of the defect. For 1 plus eta, both 1 and eta have expectation value 1, so the G function is 2. For n, you can show from the fusion rule that I displayed before that the expectation value of n is square root of 2, and square root of 2 is less than 2. So might it be that the result is n? Well, the answer is no, because it's not allowed by defect anomaly matching. Because 1 plus eta, that is symmetry reflecting under the Z2 symmetry, has trivial anomaly. There is no way of getting a minus sign when I exchange to eta topological line on a defect. But as I showed you here, n has a non-trivial defect anomaly. So by this very simple argument, we conclude that the defect must be an interesting conformal defect in the infrared. And in this example, this can actually be verified quite explicitly. Okay? Questions? So if not, yeah.
So in this case, 1 plus eta is m squared, right? And n is Kramer-Svanni duality.
Okay.
So is the new defect you're defining just the same as basically taking a slice where you do duality and then the
So sorry, you can think about it. You can think about it. Yes. Yeah. I think that this is sort of the point of view of this paper that appeared a couple of weeks ago. They do that. Yeah, exactly. So, okay, the quantum dimension is something that you can only define for topological defects. The G function is some quantity that can be defined for any conformal for any defect, and that must be topologically decreasing and coincide with the quantum dimension only for topological defects. Okay, but yeah, then there are various proofs of the G theorems. You can use like entropic arguments or more standard arguments. I can give you a reference if you want. So in the remaining 15 minutes, let me go to the last part that is about this work in progress. And I will still try to use some symmetries to understand the space of defects. But the funny thing is that now we will use symmetries that are not there. And I will explain in a while what do I mean by that. But now what we want to understand is what we can say about conformal manifolds of defect conformal field theories. As you know, the typical lore is that CFTs are discrete. It's very rare to have conformal manifolds, because when we have a marginal operator in some CFT, generically when we add it to the action, it will get an anomalous dimension, and it will not stay exactly marginal. Unless there is some special property, like supersymmetry, or there is some symmetry protecting the anomalous dimension of this operator. So the typical lore is that in absence of some symmetry, we don't expect to have conformal manifolds. And in general, I mean, strictly speaking, conformal manifolds of CFTs are extremely rare. There is a huge debate whether there exists non-supersymmetric conformal manifolds in dimension greater than 2. But what I want to discuss now is defect conformal manifold, namely situation in which I can start from some conformal defect in a CFT, and I can deform it and have a continuous family of conformal defects. So I want to add an exactly marginal deformation on the defect. And as I already mentioned at the beginning, the situation is a little bit better than conformal manifold of CFT, precisely because, as was pointed out in this paper, if I have a continuous symmetry of the bulk that is explicitly broken by the defect, then the tilt operator is an exactly marginal operator. I have a continuous family of conformal defect that exactly are obtained one from the other by acting with the symmetry operator. So you have an exactly marginal deformation. I can turn on tau on the defect, and this will not acquire anomalous dimension, and I have this continuous family. So the general belief is that now maybe it's true that whenever I have defect conformal manifold, I must have some symmetry, some continuous symmetry of the bulk that is broken by the defect, and I get this manifold. But the funny thing is that if you just look at the simplest example, that is the Ising CFT, it has three families of conformal defects that are obtained by perturbing the three topological defects with epsilon. Epsilon has dimension 1, so it is marginal, but it turns out to be exactly marginal on the defect. However, there is no continuous symmetry in the Ising model. So what's going on? We cannot understand this epsilon as a tilt operator of some broken symmetry in the bulk. And the answer turns out to be very simple. Well, in this example, maybe you can explain this in many different ways. Maybe you can say, well, epsilon is also charged under Kramer's-Van duality, so it has vanishing 3-point function. And if I start doing conformal perturbation theory, since the 3-point function is vanishing, then this will not acquire an anomalous dimension. You can run an argument like that. But I want to provide a different point of view that is much more general and will allow me to discover new defect conformal manifolds. And the point of view is the following. One way to think about conformal defects in CFT is by the folding trick. So a defect can be viewed as a boundary condition for the folded theory. I can have a defect separating CFT1 from CFT2, and this is the same of a boundary of CFT1 times the orientation reversal of CFT2. Okay. So the lore, the general slogan is that conformal defects are the same as conformal boundary in the folded theory. But it can happen that even though the parent theory, so here in general I'm allowing two different CFTs on the two sides, but we can also think that it's the same CFT. We will have an example of both. It can happen that even though both these CFTs don't have continuous symmetries, like the Ising model, it can happen that the double theory have a continuous symmetry. You shouldn't be too much surprised about it after all, no? Because a free real scalar has a Z2 symmetry, but twice a free real scalar is a complex scalar that you want symmetry. So, but what might be more surprising is that this can happen beyond free theories. And we call this phenomenon a phantom symmetry because it's a symmetry that is not there in the original problem when we discuss defects in some CFT, and we don't have any continuous symmetry. But it's a symmetry that is only arises in the double theory, and is able to constrain this defect conformal manifold. And I will explain in a while. So, and I think this is precisely what happened also in the Ising model. Okay, after all, the Ising model is essentially a free fermion, so you are not very surprised by this. But I will explain some interacting example. Because the Ising model, so in the Ising model, when I take the double Ising times Ising, it's nothing but a compact boson at radius equal to 2 on the orbital branch. And this has two continuous non-invertible symmetries that are the non-invertible vector of winding and momentum. And the two have a mixed anomaly. So when you look at boundary conditions that preserve the symmetry, at least one of the two must be broken. And this explains the defect conformal manifold, right? We start from the Ising model, even if you don't know to do any computation directly as these very smart people in the 90s. Now you can just say, okay, I start from the Ising model. I take Ising times Ising bar. It has two continuous symmetry with a 't Hooft anomaly. One of them must be broken by any boundary condition. And I conclude that there is a continuous family of boundary condition. And when I unfold the theory, I get a continuous family of defects. This phantom symmetry here is non-invertible. Why is non-invertible? Well, okay, here you see this expression that is constructed out of cosine, and cosine times cosine is 1 plus sine, maybe, or 1 plus cosine, never remember. But anyway, it has a non-invertible future rule. But another point of view that will be more useful for me is that the corresponding current, that, for example, let me focus on the momentum current, is a non-local current, because here I'm on the orbital branch, so I'm gauging the Z2 symmetry that sends phi to minus phi. So this current doesn't exist by its own, but must be attached to a line. So this is a picture that is very similar to the one that I was showing before. And when we have this non-local current, it doesn't make sense to just integrate them on a line because they're attached to some topological line, as I was already mentioned before. But what I can do, however, is the same trick I used before. So I first construct this additional topological line, 1 plus theta, and now on this topological line, this Jm becomes local, and I'm able to integrate it. Okay? And you can check that the operator constructed this way, it's exactly this one. Good. So we can look for non-local current, right? We can look for non-local currents that only arise in the double theory. So this is a game that you can have fun playing with, and we're doing it in 1+1D CFTs, where everything is much more under control. And indeed, what happened in 1+1D CFT is that CFT2 bar is nothing but the same CFT where you exchange left and right movers. So you exchange H and H bar, right? So we can start from two different CFTs, and we look at twisted sector operators in the twisted sector of Z2 lines. So why Z2 lines? Well, Z2 lines, because we want to look for U1 symmetries, but you can look for more general lines. It's more complicated, but the simplest possible thing that you can do is to look at twisted sector of Z2 lines. And if we find in these two theories two primary operators, phi H1 H1 bar and phi H2 bar, such that H1 plus H2 bar is 1, and H1 bar and H2 are both 0, then we can construct this phantom current. Because this becomes a chiral anamorphic current, so it's conserved. It only arises in this double theory, right? And in general, this current will lead in a twisted sector of some Z2 times Z2 symmetry. And it gives to some continuous non-invertible symmetry of the double theory that is absolutely not there in the original theory. And you can easily argue that this phantom symmetry must be always broken. So this will always give rise to some defect conformal manifold. And indeed, there is another operator that you can construct that is marginal, that is obtained, is an operator that is marginal now in the unfolded theory. So in C1, in CFT1, CFT2, not in CFT1 times CFT2 bar, that is constructed out of the same pair of operators, but just in this way. But this is now marginal for the same reason as this one. But if we didn't have this argument of the folding and this phantom symmetry, there was no reason why this operator should be exactly marginal. So there should be no reason, apparently, why by adding this operator on the defect, we don't generate an anamorphic dimension. But now we understand why. We understand why, because this operator is secretly the tilt operator of a symmetry that is not there. But in some sense is there, because it tries when we use folding trick to study boundary condition of the folded theory. In this way, we can generate many conformal manifolds. Yeah, we can play this game, for instance, in rational conformal theories. You can ask whether there are conformal manifolds of interfaces between SUN1 K1, level K1, SUN2 level K2. And you can show that this phantom symmetry arises if this equation is valid, N1 K1 plus N2 K2 is equal to 8. Clearly, there are a finite number of cases. Here I listed all the cases. Some of them are interfaces between free theories, some of them are not. But then you can play more general games and changing what are the CFTs in the bulk. You can look for more general WCW models, or maybe even non-rational CFT. There are many things that you can do. And we are starting exploring what are the possible landscapes. Yeah.
The first two lines will consider anomalous nature on both sides, or so for the first two lines, because they have a one quarter spin, are you look at anomalous D2 or anomaly free Z4?
I think they're always sorry. It can be anomalous, it's fine.
Yeah, but it could also be a Z4 symmetry, just not too big.
Oh.
Just staring at the spin.
I see. Yeah, it might be. But it's fine. It's fine.
It's not, yeah, I think either way is fine, I just want.
Yeah. It's also a problem. The only thing in which there could be a problem, and we have a look at it, is when the current lives in the twisted sector of a non-invertible line. In that case, and especially an anomalous non-invertible line, in that case, we don't really know whether we can define this phantom symmetry or not. So we are staying a bit away of that case. But there are many cases in which we restrict to the simple cases, so it's fine. So, okay, let me conclude. I try to convince you that studying symmetry can provide very strong constraints in understanding the space of extended defects. On the other hand, extended defects are very interesting probes of quantum field theory. So, like concatenation of arguments, it's very interesting to keep studying symmetries even in these more general problems. We can learn about even just QFT by itself, not only studying symmetries of the QFT, but studying symmetries of the QFT with the insertion of defects. I hope I convinced you that these symmetry reflecting defects are quite interesting, because by itself they have quite nice properties, and also they provide a very simple but extremely powerful tool to discover new non-trivial conformal defects. And I already discussed the simplest example here, the example in the Ising model, but we have many other examples in our paper, even in higher dimension. In higher dimension is of course much more complicated. We have a perturbative large N analysis of this QED3 example at large enough that I was mentioning. This provides actually prediction in the case of lower value of NF. It would be nice also to verify them, but I don't know how. And another question is to try to, for instance, generate symmetry reflecting data that are symmetry reflecting with respect to some non-abelian symmetry. And we found a way to do that. And using this technique of the slab gauging, and people familiar with generalized symmetry, they know what I'm talking about, but here it is more general. I can have some continuous symmetry in the bulk, and I can try to gauge it only in a slab. But gauging dynamically now, it's not a finite symmetry. So I do this, and I will trigger an energy flow in this lab, and I can close this lab, and this will define for me a certain defect. And if I have some G symmetry in the bulk, I gauge in a slab a subgroup H. In this way, I can construct a defect that is symmetry reflecting under H, for the very simple reason that topological operator of the H symmetry from the bulk just disappear inside this lab, so they can be absorbed by the defect. And it's interesting to ask what are the reflection and transmission coefficient of this defect. This can be rigorously defined in 2D CFTs, and it's a work in progress we're discussing now. Because as I told you, these symmetry reflecting defects are generalization of defects that are purely reflective, but only in the symmetry sector. So it's interesting to ask, can we find defects that are not purely reflecting, but are reflective only in the symmetry sector? And this requires computing these coefficients. And this slab gauging construction turns out to provide examples of this. And another question that you can ask is about fusing conformal defects. This is something that people are discussing a lot these days. You can put two parallel conformal defects and try to fuse them. And you can ask whether, so this is in general a very complicated problem. There are a lot of UV divergences that you have to regulate and so on. But it seems, I was talking with people that are doing this computation, it turns out that if the defects are symmetry reflecting, there are many magical things that happen with this fusion, and it would be interesting to analyze more what is the general structure, how these properties imply some simplification in this question. And regarding the last part, I think I don't see any reason why this phenomenon of the phantom symmetry shouldn't also arise in some higher dimensional example that is interactive, even though clearly it's more hard to find example. But I think it would be very interesting to find examples of this in higher dimensional CFTs to discover new defect conformal manifold. Okay, let me stop here. Thank you.
Sorry, I'm still confused on that example. So if you go to the spin, so the operator you would construct, like the exact margin operator you would claim to move along the defect movement, right? That's like scaling dimension a quarter, like 3/4, right? It's
Yeah.
not a like it doesn't have integer spin, not a problem. It's not local.
Oh, right, but it becomes local on a given topological
Oh.
defect. Sorry, I wasn't completely clear about this. So sometimes it is not necessary that the deformation happens on the identity defect. It can happen also on a non-trivial topological defect. Of course, yes, this is
When you start with a null.
that's right, that's right. Yeah. Any questions?
It's just a very basic question about the double symmetry when you have the coefficient one defects, like just in the simple case where you have the Z2 in the bulk, but it comes Z2 times Z2. Like say I put the theory on a circle in a transverse direction, like so that I'm not allowing myself to have an infinite face to the left and to the right.
I see.
Like just intuitively, how do you think about the double symmetry?
So let's say you want to put you want to say on a torus, for instance.
Yeah.
I think that the defect still feel the double symmetry because you're putting on an orientable manifold, so it knows whether something is ending from the left or something is ending on the right. But more generally, even if you want to think about distinguishing left from right, I think the right point of view is that there are more background fields. Right? A background field is a certain network of topological defects. In absence of the symmetry reflecting defect, I only have network of topological operator that I have like trivial junction, but I cannot have a topological operator that just ends somewhere.
Right.
Now, in presence of the defect, I can have this more general configuration, so I have more background fields.
I see.
So I have more background field, I have more background gauge transformation, so I can detect more anomalies.
Okay.
So yeah.
Not any other symmetries either. Yeah, if not, let's like move again.